Hi, my name is Mohit and I lead the AI research and optimization team at Stillwaters AI. And in this short session, I'm going to talk about the vector semantic search engine that we built. Now, you might think not such a unique topic after all, but the way we've built it with a lot of hardware awareness. The way we have built, it aligns with the physics of CPU caches, CPU prefetches, SIMD instructions, atomic instructions, the way they work, of course, the GPU tensor cores. And the way we have designed it, it no longer fights the hardware, but it kind of flows with it. Now, any exercise of this kind requires you to observe the system, because without observation, you don't know what's happening. So what tools of observation, what is the latency, what is the throughput vis-a-vis the industry standard, and last but not the least, the algorithms, instructions, observability software all put together, we analyze the complete process. Now this complete hardware aware design process with all the four circles I was talking about earlier, the instructions, the software, the algorithms, and the observability tools, all put together, the complete design process has been modeled into a course in collaboration with the IITs. And this is one of the course in that suite of courses. So the course is called System Architecture for AI. And you can get the details of it from our website or from the IIT's website. We'll put the link in the description below. More importantly, when you see something real like a vector database performing the way it does in terms of latency and throughput getting built, then you take the course a lot more seriously. But why is hardware awareness important? Well, this is why. But don't the compilers take care of it? I mean, they do to a certain extent, but the chips have been getting really complex and generic. Okay, so for a compiler, for a general purpose compiler, to come in and take care of it no matter what has been a real big task. Okay, so as an engineer, you have to step in. All right. Mechanical sympathy is a more fancier term for hardware awareness. Basically, what it means is all your fancy structures, object orientation, it's all very good so long as it doesn't interfere with the raw access times of my structure. If it does, I'll get rid of it. When building vector databases accessed by tens of thousands, even hundreds of thousands of users at the same time, the locking semantics has to be just right. If you're using old mutexes, well, that's the end of the story. Even if you're using hardware instructions, there are general purpose instructions and there are specific purpose instructions. So for a very specific use case, say for example a spin lock, if you're using a general purpose hardware instruction, despite being a hardware instruction, you might be losing a few cycles. Those few cycles compounded over hundreds of thousands of requests result in huge delays. So we will learn picking and using the right instruction. We will learn how to utilize SIMD acceleration. We will learn what false sharing is and how do you protect against it. Last but not the least, Stillwaters vector search built on top of Usearch, an open source product. It optimizes vector search by mapping flat contiguous memory graphs forcing explicit SIMD slices and relying entirely on lock-free bitwise traversal to make the query performance as fast as you're going to be seeing it. Now, we make heavy use of visualization to get a drop on how the stuff works under the hood. I mean everything. The hardware instructions, the algorithms, the software, observability tools, everything. And we share the same with you. Now what this does is that it makes the stuff really interesting to watch and to use, keeping the barrier to entry very, very low. So my guess is that whether you are starting off or you've been in the industry for a long time, for a longer time, you should still find this easily digestible. But let's look at the vector search first. It's also called a semantic search, vector search. In the olden days, we used to call it the fuzzy search. Some people just call it the AI search. So what is a vector search? So a vector search is something wherein you can search different modalities. For example, you can search images, videos, text, logs, anything with either voice or text itself, and it does a similarity match. It doesn't do an exact match, and it is one of the core pinings on which the LLM tech is built. So for example, if my LLM was trained sometime in January, and if I would want to know who's performing well in a cricket match that happened just yesterday, obviously the LLM has no idea about it. So the information about the match is stored inside the vector search. Your query, who performed well in the match yesterday, is taken, fed into the vector database, a similarity match is done, and the results which are returned is fed into the LLM, so the LLM weaves a story around it. So that's the long and the short of it. Now let's show you what the Stillwater AI vector search can do. So I have a couple of examples here. I have around that many images right now, and I perform multiple vectors. So the first one is exotic fruits in punchy colors, or neon signs at a gas station, girl wandering alone in the forest, and various different queries. You can write your own query as well. So for example, I can say something as ridiculous as a pink dog, and it does a similarity match. You could also do an image to image search. So for example, I can do an image to image search, which basically means show me images which are similar to it. So I could upload an X-ray and it shows me all similar X-rays. Now we've taken this vector search and trained it on medical images. So I could say something like show me Mohit's pinch view X-ray, and it returns me all the right results or similar results. Now you might think this is the main story, but the main story is somewhere else. Now when I ran these searches, I traced and looked at I traced and published the latency of all the searches that I just performed into a tool called Jaeger. And let's take a look at the latency here. So let's look at the last 20 results. And here is the real story. The latency of all these searches is, roughly speaking, around 60 milliseconds. It goes down to 60 microseconds, 25 milliseconds, 57 microseconds. And a lot of this latency that this tool is showing me is got to do with the front end tools. So we're using Streamlit right now. So if you subtract the Streamlit latency, if you just benchmark the latency of the vector search that we've built, it'll be a lot less. Now show me a vector search in the market which is anywhere less than 150 milliseconds, if at all. Now if I look into this search, the actual search is just 2.72 milliseconds, the actual vector search. Rest of it is the latency of like I said, the front end too. The NoSQLs and vector databases, they have a very similar storage architecture. Even regular databases for that matter. The thing that you need to understand is that the additions and the removals can happen anywhere, and that cannot be controlled by the software because that's happening on behalf of the users. Problem is, this data is stored, this sorted data is stored in the disk, and because the additions and the removals can happen anywhere, that requires random I/O. Now all of this is controlled by a data structure called B plus trees, which is all very good and gives me a n log n search timings to reach the elements for removal and addition. Problem is, because of multiple threads, while the structure is under modification, you've got to keep the structure under lock. And that's where your n log n goes out of the window and it starts to get dominated by the lock timings. When you bring portions of this data into the memory, it is controlled by a structure which all of us know as binary trees. Again, log n, fantastic. But so long as you're only reading, the moment there are writes, removals, additions, you again are dominated by your lock timing. So the log n goes out of the window, and you start getting dominated by the lock timings. So the real value addition here is making sure that we can avoid these two. We can avoid the locks and we can avoid, random I/O to the disk. Let's see if we can do that. Now, when we talk about hardware instructions, algorithms, software, and observability, right now all these 4 circles are empty, but we'll fill them up and let you know what comes in where. So you get a good idea of how they work, together. As I had mentioned earlier, well, there are 2 big, performance killers. One is the random write to the disk, and the other one is holding a lock. When you combine the 2 together, you have got a complete recipe for disaster. I'll skip the I/O demo today and get straight to the hardware instructions. So we'll take a look at a few of them, and we'll see if they are appropriate and what kind of performance they kind of buy us. The OSs have had, mutual exclusion as a part of the stack for a really long time. The problem is they are a little cumbersome to use and a bit inefficient. So as a generic replacement for them is this instruction called compare and exchange. On x86, it's called CMP XCHG, compare and exchange. You also have alternatives for this in other architectures, so that should not be a problem. Now, how this works logically is you cut out the OS stack and you have an hardware instruction which is going to change a value in the memory, and if it's able to change, you go ahead with your logic, and if it's not, you kind of spin. So if you take a look at this example, you've got a blue thread and a pink thread. There's a value in the memory 30, and we need to, both the threads are wanting to increment a counter. So, increase by 1. Both attempt this instruction, which is kind of abbreviated to CAS, compare and set. What happens is that the logic of the instruction is if the value, basically we pass 2 parameters, the expected value and the new value. So both of these, the blue and the pink thread on the left hand side, they attempt the CAS instruction with a 30 and a 31. They both want to increment it by 1. And the logic is if the value in the memory matches the 1, which is the expected value 30, then change it to 31 and return the old value back. If you're not able to change it, then in that case, do not attempt to overwrite on that and just come back with the new value which is existing. So in this particular picture, you see that the pink one is able to change the value, and the blue thread comes back with a, with the new existing value, and a comparison on the application side will tell the thread that, okay, your attempt was not successful, so either you retry and you probably succeed in the next couple of times, or you keep spinning if you don't. And if you see on the right hand side, the blue attempts the cast instruction once again and it's able to succeed. Point here is that there's no lock involved, there's no suspension of threads involved, so a lot of the software red tape that you had to go through via the operating system can be cut out, and this can be a lot more efficient than the traditional mutexes that have been offered by the operating system. So are we really lock free? We aren't really lock free, because that compare and set is under a lock, and that is a hardware lock. The other thing is that with the traditional mutexes, the thread often gets suspended. Now here the thread is not getting suspended, but it's still spinning. So there is no block per se, but you are still spinning. This generic hardware instruction, generic locking, you can say, hardware instruction, is a great alternative to your traditional locks, and while still not ideal, it's actually a great improvement. And because it's happening in the hardware, it's a lot more efficient than your traditional locks. The next one, which is called the XADD, is my personal favorite. So the idea is still the same. We have a value in the memory, and it's currently at 30, and there are 4 different threads with different colors. So there's a blue thread which wants to increment the counter by 4, the yellow one wants to increment it by 3, the blue one wants to increment it by 2, and the pink one which wants to increment it by 1. So all of them attempt this XADD instruction. Again, this is on x86. You've got alternatives to this in other hardware as well, in other hardware architectures as well. Let's take a look at how this works. Now, so what happens is the blue succeeds. The logic of the instruction is, it doesn't matter what the value is right now. There's no comparison happening. So whatever is the value, so the blue thread does take a lock. It's again a hardware lock. The previous value was 30. It has to increment 2 to it, make it 32. So it makes the change, writes it in memory, and returns the old value back. Now there's no comparison that happened here. Once it releases the lock, the other 3 threads, remaining 3 threads, they think, oh, we have lost the race, and we've got to retry once again. So the hardware instruction says, no, that was the old one, this is the new one, there's no retrial here. And they are surprised, pleasantly so. What happens next is the pink one takes the lock next, increments the value from 32 to 33 by 1, because its incremented value was supposed to be 1. And the older value on which the increment was done is returned back to the pink thread. So you see, there's no waiting which is happening here. There's no spinning, there's no comparison, and there's no real waiting which is happening here. More on that waiting part in just a bit. The yellow succeeds next. 33 plus 3, 36, writes it in the memory, returns the old value back, and the last one, 36 plus 4, 40, and returns 36 back. So you see what's happening is, this is called a wait. This is a great example of what is a wait-free algorithm, and completely executed on the hardware. Now what about that waiting part? Well, on most hardware, the way it's implemented is that most of these threads, they execute NOPs, no operation. So they are waiting. They might be waiting for a very short time, and that short time is by executing a kind of a dummy instruction. But there's no coming back to the software, there's no going back to the loop, there's no loop, and there's no comparison. Now if I compare these two, so we have benchmarks, and we'll talk more about more detailed benchmarks later. So you compare this with the benchmark in a 2-thread setup. You see that the XADD, which is the first one, is marginally ahead of the compare and exchange, and that marginally ahead makes a big difference because it's just 2 threads. You add more threads to it, and of course the XADD starts to pull away. So we have another example here. This time it's with 12 threads, and you see that the text XADD, well, the number of nanoseconds per operation it takes is a lot less, maybe 4 to 5 times less than the one which is compare and exchange. Both these instructions are a great alternative to your traditional locking. And if I had to compare the two, compare and exchange is a great, you can say, generic instruction with which I can build all kinds of different locking paradigms. For example, ticket locks, spin locks, mutexes, counters. And XADD, on the other hand, is definitely faster, definitely quicker when I want to build a counter. Now, if I had to functionally compare the two, then I would use compare and exchange, and it will be absolutely irreplaceable if the value at which I'm attempting a change is not negotiable. So if 30 is the value where my change must be done, then I cannot replace compare and exchange with XADD. On the other hand, if all I'm interested in is the change, but where exactly the change happens is kind of negotiable for me, then XADD is the way to go. To put that in perspective, if I'm going for a movie and the seat that I want is not negotiable, I would have no choice but to go with compare and exchange. Otherwise, I could go for XADD. Now, all of these are great additions, but what do I use them for? If you recall, the premise that we started with is the two big performance killers in terms of a vector or a NoSQL database is, avoiding random writes and avoiding logs. So can we build structures? Can we build data structures with which we can avoid these two? Now, one of the things which is vital for most databases is a log. A log keeps track of what's happening. It's a persistent log saved to a file. So in case my database crashes, I know I can fall back on the log, and when I replay the log of what has been stored there, I can reconstruct exactly where the crash happened, or right before when the crash happened, I can continue forward. So let's first take a look at this log. Now, with a log, regular stuff, you've got to take care of. You don't want the two threads on behalf of two threads. One thread's entry shouldn't write on top of the other thread's entries. Way back in the past, we used to protect this with a log. So let's see if we can build this without a log. Now, the first thing we do is that we memory map a file from the disk to the memory. Now, what is memory mapping? That's beyond the scope of this discussion. Give a Google search, you'll know what I'm talking about. So we bring a file up from the disk to the memory using memory mapping. And this is essentially the log file. And where exactly the write is being done by a thread on behalf of a client is controlled by this XADD counter. So as of now, the counter is at 0. And if you recall this picture once again, there are 4 different threads on behalf of 4 different clients who are wanting to write the log entry. So let's say one wants to insert element X, element Y, whatever. So the 4 threads, they want to write to the log on behalf of 4 different clients, and their log entries are of different sizes. So the green thread's log entries of size 4, and so on and so forth. Right now, the counter is at 0, and thread 3 succeeds, the yellow thread succeeds and makes the counter value 3. The value which is returned back is 0. Remember, XADD returns the value at which your counter was incremented. So, point I'm trying to make is the yellow thread knows that its increment was done at 0. Size of its entry is 3. The counter value now is 3. So it now knows that from 0 to 3, that portion of the file belongs to it for it to write its own log entry. And while it has not even started writing yet, the blue thread succeeds, increments the counter from 3 to 5. The value which is returned back to it is 3. So it knows that its portion where it has to start writing from is 3 plus 2, 5, and that's the size of its log entry. And while both these threads haven't yet started writing even now, well, they now begin to start writing. So the yellow thread starts writing from 0 to 3 and the blue thread starts writing from 3 to 5. All of this is happening concurrently. No one is taking a lock and no one is waiting. The green thread comes along and it does its own request. The counter, which was at 5 plus 4 makes it 9. The value returned back to the green thread is 5. So it now knows that from 5 to 9, that section of the file belongs to the green thread for it to write its own log entry. Okay. Last but not the least, well, the pink thread succeeds finally, and the value was 9, increment 1 makes it 10, return value is 9, so it now knows from 9 to 10 is the section of the file which belongs to it. So you see what's happening. 4 threads, no locks, absolutely wait free, no spinning. Everyone is writing concurrently, probably parallel depending on how many threads there are, how many hardware threads there are, and all of them. So this is what we call as a wait-free log. Logs are great for crash retrieval because the idea of a log is to store data in the order of arrival. So in case something goes wrong, you replay the log and you can reconstruct the system state like it was before the crash. But I cannot search the logs. So, and the whole value addition that a database brings to the table of any kind is that you're storing data based on some kind of an index which is sorted so that when you search, it's a lot more easier, quicker to search. Traditionally, we've used red-black trees. Now, as I said earlier, red-black trees are great. They give you login times, search timings. Problem is when you take a lock. When you take a lock, everything goes south and you get dominated by lock timing. So, do we have a replacement? Let's take a look. So, we'll take a look at what is a skip list. It's a fantastic structure. And a slight modification of this is what is used in vector databases. So let's ensure that we get this absolutely right. Now, let's have a layman understanding of what is a skip list. So let's assume that we have a metro in Bangalore, and we have, let's say, 10 train stations. So let's say that there are 10 metro stations and they are sorted based on the distance. So the first one key is 10, second one key is 20, let's say 20 kilometers away, and so on. Keys 30, 40, 50, 60, 70, 80, whatever, 90, 100. So these are metro stations. And let's say my office is somewhere here next to the station 10, for lack of a better word. So at the end of the day, I get down, board the metro, and let's say my home is somewhere around 80. So I take the metro, get down at 80, and take a short walk to my home. All very good. Problem is, there are too many stops for people beyond, let's say, 4 or 5 stations. So beyond the 4th and the 5th station, because the rule of this is that it stops at every possible metro station. All right. So people who are beyond 4 or 5, they got to wait for everyone to get down before their station comes along. So an arrangement is done, and let's say the people of the city, they petition the government and they say, look, do something about it. It takes a long time for us to get to our station. So the government does something and it adds another metro. The rule for this metro is that it stops at roughly half the number of stations than the train below. So this metro stops at every possible station. The one above stops at roughly half. Now you might be wondering, how do we get to this roughly half? But more on that later. And now when I have to get to station, let's say 80, I take this new super fast metro. I see if my station is beyond the next or right one. So the next one is 20. I have to get down into 80. Again, I take the next one, take the next one. So the next now is at 100. Of course, I'll go past my 80. So I move down and then I get to 80. So you see that as an improvement in my travel time. We are very happy with this new arrangement, and we again petition the government and say, "You've done a fantastic job. Can you do more?" And the government listens to us and then adds 2 more tracks. Maybe you can call it the super fast track and the turbo track. Now, if I've got to get to 80, and each subsequent metro stops at roughly half the number of stations than the train below, than the metro below. So this stops at all 10 of them, this stops at 4 of these, this stops at 3 of these, and this stops at just 1. So roughly half, not exactly half, roughly half. And if you take a look at it again, it's not alternate, it is not even, it's not odd. The only way to aptly describe it is roughly half. So now when I have to get to 80, I start at the turbo track. See my next station in this track, it's 100. Obviously it goes past 80, so I don't take this track, I move down. Look at the next station, it's 40, I take it. Look at the next station, it's 60, I take it. Look at the next one, it's 100, I don't take it. Move down. Look at the next one, it is 100, don't take that. Come down and I reach 80. So that's what is a skip list. So what's a skip list and why is it called so? Each of these various levels is a list, and the list, as you move up the list, it skips some of these train stations or some of these keys, as you might want to call it. Now, how do we search and what are the search timings? So search timings, I already told you, it's roughly log n, and you squint your eye. Why roughly log n, and how do we get that roughly log n? Well, it's roughly log n because each list as you move up is carrying or stopping at roughly half the number of stations than the list below, which is why it's roughly half, not exactly half, roughly half. So the search timings here is roughly or nearing log n times. Now you might wonder, we have a red black tree which gives me log n times, and here is a structure which gives me nearing log n times. Why would you ever opt for this? Well, that's the part which is the best part. So that's your search. That's your search traversal. Now, how do we do an add? So this is where the real story unveils. Now let's say, because this structure takes no locks, and let's say there are 2 sets of people. So let's say there is a place in Koramangala, there's a place called Koramangala, great for, has got great restaurants, so I picked that place. So there is a locality, or you can say a locality called Koramangala, and for lack of a better name, let's say it is at 86, its distance is 86, so its insertion point is between 80 and 90. And there's another one called Indranagar, again great restaurants there as well, which is at a distance of 85. Again, its insertion point is between 80 and 90. Now, if there was a global lock, I would know that the other set of people, so the Koramangala people would know that the Indranagar people are trying to insert at the same insertion point and vice versa. But because there's no global lock, there's no way to find out if, so the Indranagar people are blissfully unaware of Koramangala people, and the Koramangala people are blissfully unaware of Indranagar people. So what they do is they construct their node and make their next pointer point to the 90. Both of them happening nearly at the same time. So they both end up constructing their nodes and their next pointer pointing to the 90 node. Now, what they have to do is they have to swing the 80's next pointer to their node. Now, 2 people attempt this at the same time. Now, ordinarily with a lock, this would be very easy, but we know the problem with the lock. It's very, very slow. Okay. So what they do is that they use compare and exchange to make this change. Both attempt compare and exchange exactly at the same point, and their expected value is the existing pointer from 80 to 90, and their new value is the pointer to their constructed node. But as you know, only one of them can succeed. So one of them succeeds. Let's say the pink one succeeds. The Koramangala people succeed because they were maybe a little faster, they started a little early. Now, so when they succeed, the 80's next pointer starts pointing to the pink node, the Koramangala node, but the yellow node, the Indiranagar node, they are returned back the new value, which means when they do a comparison, they figure out, all right, somebody has changed the pointer from underneath our feet, so we need to try once again. So they come back. And do a retrial. But that retrial is in the next couple of slides. In the meanwhile, the pink one has done the insertion. The problem with the Indiranagar node now is because their distance is 85, their insertion point has changed. It's no longer between 80 and 90. It's between 80 and 86, which is the Koramangala pointer. So now, before we get to the Indiranagar people once again, let's take a look at, should we add this node to the higher levels? So should we add this level to the higher level? Well, there can be many answers for this. One is yes. But then if it's a yes, everything will get added up to the high levels. Other answer could be no, obviously not. Nothing will ever get added to the high levels. Third answer could be depends. So depending on how many links are already there, you can add it to the next level. But the problem with this answer is that you don't know which nodes that the higher links are carrying because you don't have a lock. So because you don't want to take a lock, you can never find out how many links are already existing in the high level nodes. Because as we speak, or as you're attempting to find out without taking a lock, those links may be changing. So a link which may be there, it could be getting removed, and a link that might not be there could be getting added as this attempt to find out whether links are there at the higher levels or not is going on by the pink thread. So it looks like yes is not the answer, no is not the answer, depends is also not the answer, and we cannot take a lock. So this is where the brilliance of the structure comes in. So what it does is it has to look for a solution which is local. Okay. So how can we locally understand whether a link has to get added up in the higher levels or not? So the answer here is that we do a toss of a coin with, let's say, probability 0.5. So if the toss turns out to be right or true, then you add that link to the higher level and you do a toss of a coin once again to keep continuing adding it to the next level, and wherever it turns out to be no, you stop. Now because the probability, the value of that probability happens to be 0.5, this structure has got this fantastic property that the number of links which are available at the lower level, only roughly half the number of links get added to the higher levels. Right, now the Indiranagar people are back again. Their insertion point has changed and the steps are exactly the same. So they construct a new node, make its next point to the newly added Koramangala node, and they want to swing the 80's next pointer, which was so long pointing to the Koramangala node, you make it swing to its own node, and then add this yellow node to the higher link depending on the toss of a coin once again. The point I'm trying to make is this. The reason why there was a retrial here in this particular situation is because the insertion point was the same. But if the insertion point was different, there would be absolutely no, the threads wouldn't even detect that there was addition or removal happening at other portions of this particular list. So skip lists are great replacements for red-black tree in concurrent situations. So you can still go ahead and use your red-black tree or any other binary tree, so long as the number of threads are just one, or wherever contention and lock timings don't matter. But if there are multiple threads And if there are modifications happening, it's not a read only, then you've got pretty much no choice but to replace your structures with skip lists. Now, let's combine the two for a lockless or a wait-free VectorDB storage. But it's just the log which is wait-free. The skip list is not essentially wait-free. But can we make it wait-free? You can, but you have to be a bit more creative in the way you allocate memory. So right now what's happening is that you have a node and you construct a node and you make it point to an so let's say if the insertion point is between 10 and 20, you make a node, you make its next point to, let's say, the successor, and at the same time if there is another thread which comes in and makes its next point to its own successor, which right now happens to be the same element, which is what we are talking about. Now, to swing this pointer either here or here, we use a CAS, compare and exchange. Can we use an XADD? Well, you can't, not in the normal scheme of things, not the way which is being done right now. What happens is, in the memory, these nodes are already allocated. And when a thread T1 comes and a thread T2 comes and they allocate two nodes, so let's say one node comes in here, this is thread T1's node, other memory allocation, and this is T2's node. Now, how does CAS know that if this fails, well, it has to update to this pointer? So, roughly speaking, the automatic increment that happens in XADD is not possible with pointers. But if we pre-allocate a tape-like storage, essentially a linear storage, and all the nodes are being allocated from here. So what happens is, these are already occupied by existing nodes, whatever, and then thread T1 comes, allocates this node, you use an XADD to allocate, thread T2 comes, use an XADD to allocate, and then you fix up the pointer. So you make this point to its successor, make this point to its successor, and then make this point to its predecessor or whatever. Okay, so if you can get creative with your memory allocation and kind of the established ideas of object orientation, if you can work around them a bit and make your allocation a bit more creative, like the way we have, you can make skip lists also wait free. Now, that being said, have we done it? So yes, but I'll show it to you with a different structure, not with a skip list, because in vector databases we don't really use a skip list. We use a derivative of a skip list. So we'll talk about that. So now let's combine the two structures that we've understood for a wait-free, write path. The read path was anyways wait-free. So let's take a look. Now, for a NoSQL database, what happens is a client comes in and executes an insert statement. So insert 1, key is 1, name is Mohit, location is Bangalore, let's say some kind of an ID is 303 into the employees table, maybe employee ID or something. Now, so step 1, you write to a log, and most NoSQL databases, they use a cell style storage, which we don't have the time to get into right now. So we'll skip that part. So the row is split up into cells. I'll skip that part right now. So the order of arrival is stored in the wait-free log, and the sorted data goes into the skip list. Right now, it's not making a difference because just one row. And the logical view is of the table. So logically, you view it as a table, but internally the storage is a little different. You may have a separate session telling you about why the cell storage is the way it is. For now, let's move on. Second client comes in, makes another insert, and same thing happens. The order of arrival when it comes to the log and the sorted data goes inside the skip list. So this is always sorted, the skip list. Now what you do is that over a period of time, when the skip list becomes large in the memory, you sync it to the disk. So the disk data is never modified. Now let's do an update. Let's change some details here. So an update statement comes along. Client 1 says change the name from M to MK, from Bangalore to Toronto, and the ID from 303 to 0035, whatever. So now again, this is broken down into cells. Both these are broken down into cells. So you see order of arrival in cell, depending on in what sequence were these update statements issued. So you see the order here is different, 1 2 1 1. But when it comes to the storage in the skip list, it's sorted based on the key, and it is 1 1 1 2. And again, what will happen is that once the data in the memory grows large, the skip list grows large, you again sync it to the disk. Now, what you could do is that when you have multiple files in this, nothing ever gets modified. So one of the strategies can be that you read it in a way that your newer values, they bury the older values. That's one strategy. Second strategy could be you could then have a separate thread which could combine these two files. So, or you could have a combination of these two strategies. So in summary, this is what we've done. This is what we've learned. This is what we've utilized. Now let's go to the vector database specifically. So what are the structures in a vector database, and how can we make them better or faster and efficient? The algorithm that we use to index and search vectors in a database is called Hierarchical Navigable Small World, HNSW, W for short. That's a mouthful, isn't it? But before we get there, what are vectors? So while that's beyond the scope of this particular discussion, I'll very quickly take a look at what vectors are. Now, vectors are, for lack of a better word, non-scalar. So multiple values to define various things. So in this picture, like you see, the x and y coordinates are set in such a way that the similar objects, similar things, they kind of huddle together. So cat and dog is together, car, bicycle, truck, those are together, apple, pear, watermelon, they are together, and so on. But who sets these values? Who sets these values? Now, these values are actually set by a neural network. So we have a setup wherein we train the neural network to understand similar things and to give similar values to similar things. Okay. How it's done, again, it's beyond the scope for now. And just like we have text embeddings, things that textually describe things, same thing applies for images as well. So again, if you see here, the picture of a dog, picture of a cat is kind of huddled together, the fruits are huddled together, the vehicles are huddled together, and so on. You can also have joint embeddings. You can also have joint embeddings wherein images, similar images and similar text, or text that describe images, or vice versa, they again huddle together. Again, who sets these values and what are the values that these vectors carry? Again, beyond the scope, but it's a neural network which is trained to do this. All right. And in this particular picture, we see that the vectors have got two values, but in practice, these vectors are quite multidimensional. That means high multi-dimensions, from a few hundreds to a few thousands. All right. And these are the vectors that we're talking about, and these are the vectors that we're storing inside that vector database. And the demo that I showed you in the beginning, those are the vectors that are being searched. So when you have an image of a cat and you give a search term that says pink cat or something, well, we do a vector match and then retrieve similar vectors. But how is a vector compared? Because if there are hundreds and hundreds of values in a vector comparison is not going to be easy. Well, without discussing this any further, we use what we call is a cosine similarity. There are other measures as well, but this is one of the ways in which we find out how alike two vectors are or how different two vectors are. More on cosine similarity probably in a different session, right? Now coming back to the HNSW, let's take a look at how it looks like firstly. And I think this makes it pretty clear why we discussed a skip list before this. So you can see the similarities, but let me tell you the differences first. The difference is at every level, we don't have a linked list like we had in the previous structure. We have a graph, and one node may connect to multiple nodes. All right. So how do we search here? So let's take a look at how we search here. Very similar strategy. Okay, so what happens in this case is, if this is my query vector, this is the kind of object that I'm looking for. I start at the top level and pick a random entry point. There's some variations here, and find out my closest neighbor. There's only one in this case in the picture, so we find that out and we drill down. We find the closest neighbor here and we drill down, and then we find the closest neighbor here. A couple of differences from the skip list to this one is, it's possible that your closest neighbor might only be close if you look at things locally. So you don't want to end up in a local minima. That means you don't want to get happy finding out your closest neighbor or the object which is the most similar to the node that you're looking at just by evaluating its immediate neighbors. Because what's possible is that if this is the node in question, it's quite possible that though this is the closest neighbor locally, as in for immediate neighbors, it's quite possible that this node is similar but not as similar to this one. So to this one, and this has got another neighbor which is even closer to the original node that we're talking about. So we maintain a list. In fact, we maintain a priority queue here, and in this priority queue we store the nodes which are similar, and this can go up to hundreds, and this is called EF construction if we are indexing, and this is called EF search. These are parameter names, and they can be slightly different names as well. EF search when we are searching through the vectors. So this is the HNSW algorithm, and the reason why we discussed the skip list before this, I think, is quite apparent. So what's the point of all this? We learned a couple of hardware instructions, we learned a couple of algorithms, we learned another one, HNSW, which is similar to skip list. So what? How do we use all this? The way we want to use all this is, we want to analyze maybe a couple, maybe start with just one. So let's start with a few vector databases and analyze them, how they perform. And one way to analyze software from a perspective of the hardware is what we call as the TMA, top-down microarchitecture analysis. Now, software has got a lot of things, There's memory, there is instruction, there is I/O happening, there's a lot of things happening. There's network which is being used, so a lot of things are happening. Now, so what TMA does is that TMA takes a top-level view and does a broad brush profiling of the application and allows me to focus on the areas which may have issues with performance. So we took the FAISS, which stands for Facebook AI Semantic Search, and the other product is the Usearch, on which Stillwaters vector search is built on. So let's first take a look at the analysis that we ran, and let's see how the two perform. So what tool are we using? We're using this fantastic open source tool called the Toplev. Toplev internally uses Perf, and with Perf you can measure a host of things. So branch instructions, branch misses, bus cycles. I won't go through it right now. Right. So Toplev internally uses Perf. Perf utilizes the hardware performance counters, which are also called performance monitoring counters. On modern CPUs, these are special registers which are dedicated for instruction profiling. So a lot of tech words in there, but just to give you an idea, we profile the application, the instructions that they are running, what's the profile of the instructions that they are running, and we do a broad brush analysis which tells us where could the issue be. Now, is it the front end of the CPU which is stalling? Is it the back end of the CPU which is stalling? Is it the serialization which is creating issues? Is it the memory access, or is the SIMD, are the SIMD registers and instructions not utilized? So there could be a host of issues. What TMA does is that give us a broad brush as to where should you be delving deeper, and where should you analyze more, where should you focus your analysis on to gather more information as to what could be going wrong or right with your application. We specialize in this part, and we are benchmarking. So this is the tool, this is the tool command, and this is the actual application. It's the actual application. So we are benchmarking FAISS, Facebook AI Semantic Search. From now on, I'll refer to it as FAISS. And this is Usearch, Stillwaters Usearch. The open source Usearch is by itself a fantastic product. But what we have done is that we have optimized a bit more on the hardwares that we support. Quite a bit more on the hardwares that we support. Now, when we analyze this, what we are saying is that you index 100,000 vectors, and the neighbor count is 100, which means one node will have 100 neighbors. Okay. The dimension of the vector is not mentioned. By default, it is 256. We mentioned what vectors are right before that. And the size of these vectors, the data type of these vectors, we try out 3 different types: 32-bit float, and FP16, BF16, and int8. So one is 32-bit, one is 16-bit, and one is 8-bit int. Now, let's do an apples to apples comparison. We have vectors indexed and the wall clock time. So obviously higher is worse, lower is better. Now, so this is your 7.2 seconds. This is what we are talking about. This is the one we're talking about here. And this has to be compared with Usearch 32. 5.2 color is deep. So this has to be compared with this. Let me change color. And then we've got the 16-bit phase. This is 16-bit phase, and this has to be compared with 16-bit Usearch, which is this one. And let me change color one more time, one last time. This is my 8-bit phase, this one here. And this is my 8-bit Usearch. You see there's really no comparison between the two, and FAISS is no slouch. It's a fantastic software. It's just that it's not designed with a lot of hardware awareness. More on that later. Now, let's take a look at the same thing. So what you saw earlier was latency. Here's the throughput. Obviously, higher is better. You search a lot higher than your FAISS. You search a lot higher than your FAISS. Now, I could go. So each of these graphs, they're telling me a story, but I'll skip that story for today in the interest of being concise, and we'll focus on a few points. So the part that I want to focus on today is this, and a couple of more things. First one, if you see here, this is the serialization operations and lock pressure, which means amongst the instructions that are being called, what are the numbers for serialization instructions? So the instructions which stall the CPU, for example, when you take a lock, which are called for, let's say, giving up the CPU if you're spinning for too long a time. And if you see here, FAISS has got a huge, you can say, the numbers are very, very high here. And the numbers here are very low. So obviously, you have Usearch performing a lot better compared to FAISS. Now, when two threads are fighting with each other, so let's say if I'm fighting with you, and if I get the lock and you don't, and if I make a modification post that, the data that I have changed, the locality in which it's located, that has to be cleared out, which means you got to flush your caches, and that's what we call as machine clears and other nukes, wherein you get rid of the data. Maybe you got the speculation. Most of the CPUs today are highly speculative, and when you make an assumption about a branch, and if that branch is actually not taken, then you've got to make sure that you clear up your pipeline, clear up your data which was there in the cache lines, and restart once again. So that costs you hundreds of cycles and delays your application. Moving on, this talks about retiring, so it means how often and what is the percentage of instructions which are being retired. And this particular picture talks about the heavy and light SIMD operations and registers. The light ones are between 0 to 4 cycles, and the heavy ones are anywhere from 4 to 15 cycles. Anyways, let's move on. This one talks about the execution ports, and with this you can get the utilization of a CPU. So a modern CPU, I'm talking about a single core here. So if I look at a single core picture, this is a 10-year-old CPU model. I think this is called Haswell. Yeah. So there are 8 ports, port 0, port 1, and each of these ports they specialize in a particular type of instruction. So what we're talking about here is those 8 ports for that particular CPU in this case, what's the utilization? And that will give you an idea of how fast your application is running. Let's do some runtime profiling first of both the benchmarks. So this is Stillwaters Usearch. Takes about 14 seconds to finish. And then we have the FAISS benchmark. Let it take its own time. Okay. So what we've done so far is use tools like top left, do a top-down microarchitecture analysis or TMA, which is a high-level analysis of the instruction profiles that we gathered for the 2 benchmarks, which is still high level and gives me an idea of where the issues, if any, may be. All right. Before that, this is the FAISS benchmark. It ran approximately twice as slow. So this took around 27 seconds, and the previous one, the Usearch, that took around 14 seconds. More on this later. Okay. So the TMA tool tells us where the various, broad areas where the problems could be. So from the slides that you saw, from the pictures that you saw, the graphs that you saw, there are roughly 2 or 3 areas where we could be, looking at. One, of course, locks. 2, SIMD instruction utilization, and last but not the least, memory. Locks primarily. So now what we're going to do is we're going to dive a bit deeper, quite a bit deeper, I would say, and we'll try and associate those issues with stack, which means what are the functions which are getting called, and can we pinpoint the problem, can we pinpoint the function or probably even the line number because of which the error could be happening. So this is the command that we've run. Perf record the frequency of the samples being gathered, and there are really 2 kinds of events that you can gather with Perf. One is the statistical events or counting events, as we call it, wherein I could say something like, can you count the number of cache misses for this application? Hear what we're saying. So that's a counting event, and that's with perf stat. So you say perf, and stat is the command for that. When you say perf, you don't specify the G with this, but when you do specify the G, what you're saying is count the number of cache misses, but also apportion it to the functions being called. So it's like this is the total number of cache misses that we've had, and out of these, this many is being caused by that function, and so on. And it's not just the function names, it's the complete unrolled stack, which means this function called this function called this function called that function, and that's how these and we apportion for every function in that stack as to how many cache misses occurred. You kind of portion there. Now there are 2 ways of calculating this graph, rather 3 ways of calculating this graph. It's not that important right now. We're using an Intel specific last branch record. That means the stack frame, the way we work it out. There are a couple of different techniques with which we do that. LBR is Intel specific way of doing that. -O says store your data there, and this is the regular Python command. Bench index, this is for phase, and the same 2 parameters, same set of parameters, like 100,000 vectors, neighboring count at 100, the default vector strength at 256. All right. Now, so we gather the stack profile. We do something else as well. But before we get there, let's keep a couple of screens ready because this takes a little time. Okay, then what we've done is we have, so let's say that our benchmarking was done for 14 seconds. Now this 14 seconds, we divide this data into sections of 0.02 seconds. So this is the data for 0.02 seconds, the next 0.02 seconds, the next 0.02 seconds, and we have 50 rows like this. So we stack, and this is configurable. The 51st second comes here, 0.02 seconds. Now for each of these 0.02 seconds, we calculate the CPU utilization, and we color these squares based on the utilization. So a deeper color means better utilization, lighter color means lighter utilization. And whenever we see, let's say, these couple of squares, they have light utilization, so I can highlight these and say, show me the stack which was on flight, while which kind of gave us this light CPU utilization. So let's take a look at the graph itself. So first things first, this is for FAISS and this is for Usearch. For FAISS, as you can see, it took a longer time. So 50 into 26 into 0.2 is the total time, and that's what it is. And for the other one, it's 14 seconds. So it's 50 into how many? 13 or 14 into 0.2 seconds. So the first one works out to around 27 seconds, and this one works out to around 14 seconds. Now, what we do next is we can highlight the portion where the CPU utilization is lighter. When we do that, it shows me the stack that was on flight for which the utilization was less. And there you go. So, and then what I can do is that I can give a search for lock. Give a search for lock. So you can see that nearly 75 to 80% of the time, the function which is getting called is add with locks. Okay. Next, what we can do is we can look at the corresponding assembly. We can look at the corresponding assembly here. So I could use this command called perf annotate. Now I can annotate the whole FAISS application, but that's too much data to look at. So what I could do is that I could say, all right, perf annotate, point it to wherever the data is stored, and give the name of the function, add with locks. So can you show me the assembly for this section of the code, or for this function to be more precise? So I could do that. Let's see if something interesting comes up. So there you go. That's the corresponding assembly for that function. And let's see if anything, sticks out. Don't worry about the assembly too much. Most of it. So it's a function where there are recursive calls to that particular function, add with locks. So it calls itself depending on various conditions. I won't go into that right now. But the thing that sticks out is unset lock, release of a lock, and there should be a lock taken earlier. So it calls an OpenMP library function which takes a lock, and a lot of code, adding of the node, associating the node with its neighbors, neighbors being associated back, or neighbors pointers associating back to this particular node. That all gets done in that OMP set lock function, within that OMP set lock section. And then once that's done, well, you release the lock. Okay, let's take a look at that particular function. So let's look at that particular function, and I've kept it ready. There you go. So in this function, the one which takes the lock has been taken using lock compare and exchange, and there's a 98.02% of the time the application spends is in that code. So the code is spinning, okay, and this also makes calls to unpause and release the CPU. You can probe further and you'll get to know that as well. What just happened? You see, design with locks is very easy. When you have multiple threads, the critical section, you take a lock and you move forward. It makes your design extremely simple to reason about. But the price that you pay is very heavy. So here's what's happening. Once a thread figures out exactly where to add, once it goes down the levels and figures out, okay, here's the point wherein I have to remove or add the node, it takes a lock, allocates memory, allocates a node, fixes those 100 pointers going out, fixes those 100 pointers pointing back, and then release the lock. So all of this while, even if there are 100 threads which want to get into the critical section, they're absolutely blocked. And this isn't just true for FAISS. FAISS is just one such software. But you take a look at any vector database, they'll have a very similar problem, because it's very easy to design with locks, very easy to reason about locks. All right, but the price that you pay is very, very heavy. Now, FAISS is itself not a slouch. It's a very good software. It's just the lock which is undoing it. But that's the whole point. I mean, if you don't use the lock, reasoning becomes very, very complex. All right. Now, the other thing that I wanted to point out is, if you look at this picture, around 75 to 80% of the time, you're calling this function called add with locks. That in turn makes a call to OpenMP libraries, take the lock, you do your section, and then you release the lock. So a good portion of the time is this function getting called OMP barrier. This is where the memory nukes happen, which means if me and you are fighting for something, and if it's the same shared data that we are fighting over, and if I've taken the lock, the data that you're interested in is also loaded in your cache lines. You've got to invalidate them, and which is what we saw earlier in those graphs, that a lot more memory nukes, a lot more memory barrier, a lot more cache invalidation with FAISS than with Usearch. Just want to revisit that one more time. So here's what we're talking about. So a lot of serialization operation, lock pressure, and this is where FAISS falls behind. This is the memory clears. That means the cache flushing that happens because of those locks. And last but not the least, as I said before, FAISS is no slouch. It uses a lot of SIMD. If you look at the SIMD utilization between Usearch and FAISS, it's even Stevens. Okay. In fact, if you take a look at this one here, for these couple of threads, it's FAISS utilization of SIMD, which is a lot higher than the Usearch. So let's move on. And what's the point of all this discussion? All right, we found out, we've learned those hardware instructions, algorithms, and stuff, and we found out that FAISS is, we know the issues with FAISS, but how do we use it? How do we utilize this? What benefit is it for us? Let's take a look. So you saw the demo, you saw this, and here's the, if you go to the GitHub link for FAISS, you can very clearly look at the function called add with locks IMPL, makes a call to lock function, lock vector. By the way, this OMP set lock is an interface, which means the compiler adds the right concurrency primitive with which the lock is finally. So that happens at the compilation time. Right. Now, the way we use this information is, now we know what ails FAISS and other vector databases. And we know what to look for. We know why FAISS and other vector databases are running slowly. So throwing more hardware at it, it's not going to help. How is it going to help? You're taking a lock. So it doesn't matter if you have a more powerful processor or actually bigger caches. So what's the solution? So solution is, either you write everything from scratch by yourself, keeping in mind what you've learned, but better still, find out libraries which are aligning with your hardware awareness and tweak them. And that's where we come in. So we found Usearch long back. We started down the path where we wanted to implement this ourselves. And then we happened to stumble upon Usearch. And then we tweaked it for our clients, for the specific hardware that our clients uses. And we've tweaked it for various different architectures. All right. So, but before we get there, let's take a look at concurrency primitives and how can we improve on CAS. Is there a better way of getting a lock and releasing a lock? Is there a better concurrency primitive that we can use? And so let's take a look at that. So before we close that section on FAISS benchmarking and profiling, I'll say this, that at least FAISS, unlike some other vector databases, doesn't use OS mutexes. Okay, so in that way, it's a lot more quicker than some of the other vector databases. Moving on, let's analyze compare and exchange. Is there a better alternative to it? See, you see, compare and exchange is a great instruction, great alternative to your OS new Texas, but it's a very generic instruction and it pays for that generality. So is there something which is more specific? For example, for a counter, XADD is definitely better. So is there something more specific, more efficient for a lock than compare and exchange? Let's take a look. Okay, see what's happening here is this is your compare and exchange, and it can implement anything. Any of these can be implemented using compare and exchange. Point is, it pays for that generality. So here's what it does. It takes the value that you want to increment, goes to the memory address, does a comparison with the value which is already existing in the memory. If it matches, of course, it takes a lock before that, hardware lock, exchanges it and returns the old value back. Now, while this instruction, while this thread, while one thread was calling this instruction, if there's another thread that makes a call, it waits for this instructions to get over, which means that if it started with the same assumption, that assumption is no longer true. So it does not modify in data and returns the new value existing at that location back. Now the thread, the two threads, they analyze the return value, and one of them knows they have the lock, the other one knows they don't have a lock. So the one that doesn't have a lock starts spinning or could do anything algorithmically. Now, so that comparison, is it really necessary? Well, we have a newer instruction called just exchange. It's meant only for locking. This is great if I want to implement a counter, lock, anything, ticket lock, anything. But like I said, I pay for that generality. Is that comparison really necessary? Because that comparison requires me to load data from the memory. All right, so is that really necessary? Now assume that I have a value 0. So this is the bit which controls my lock. So I have a thread T1, I have a thread T2. The attempt is to make it 1. So this also wants to make it 1 and this also wants to make it 1. So both these threads, they attempt a lock. Let's say thread T1 gets a lock and modifies this to 1, returns the old value back. There's no comparison. Simply writes 1 and returns the old value back, which means it takes the lock, writes the value 1, and whatever value was existing returns that back. When threads and releases the lock. Thread T2 comes, takes the lock, writes the value 1 once again. So overwrites 1 with another 1, but returns 1 back because that's the value that was existing in the memory when thread T2 came along. So in both ways, in both these cases, thread T1 knows it has the lock because it overwrote 0, and thread T2 knows that it doesn't have the lock because it overwrote 1. This comparison is not necessary. Now you might think I'm splitting hairs, but you compound this over millions and millions of calls, this is substantial. Okay, and plus the cost of comparison, loading data from memory. So all of that, if you factor that in, okay, it counts for a lot. Okay, there are some others. We'll skip them in the interest of time today. And there is a plain store. So how do you release a lock? You simply write 0 back. So the thread which has gotten the lock writes 0 back to it once it wants to release the lock. Okay, so this is how this exchange works. Right, so that's a quick summary of what we discussed. On the left hand side is the CAS, compare and exchange, and on the right hand side you've got just the exchange. So can I use exchange for a counter? Of course not. So this particular instruction is specifically built for implementing a lock without the extra cost. All right, so I'll still pick compare and exchange if the value at which my change had to be done is not negotiable. but in this case, it doesn't really matter. All right, now right, let's benchmark it. Let's benchmark it. So how do we benchmark it? Well, we could use various benchmarking tools, but the problem is that micro benchmarking is fraught with danger. Micro benchmarking is you pick a small portion of the code and its alternative, and you want to figure out which one is quicker. As I said before, the big problem here is there are multiple variables. There is CPU frequency that varies. Many of the processors, they have something called a turbo boost, wherein the frequency goes beyond a point. There are other things. For example, thread migration that has to be contended with. The compiler reorders instructions for better performance, and interference from other threads that might also impact micro benchmarking. So I think some 10 to 12 years back, Intel introduced RDTSC. So read timestamp, a special hardware instruction which counts this. Which counts the cycles, because the frequency may vary, but the cycles will not. So which counts the cycles, and there is an instruction to stop the count. Now there are two instructions here. First one is RDTSC and the other one is RDTSCP. Now this one cannot be reordered, which means that if I start this instruction, do whatever logic I have to do, and I stop this instruction, with this the instruction may get reordered, which means it may be placed after my all-important instruction, defeating the whole purpose of a micro benchmark. Okay, well, this one cannot be. So there is a tool called NanoBench which utilizes this RDTSCP, and that's what we're going to be using. So here is my NanoBenchmark, and this is the CAS uncontended. This is the exchange, its alternative uncontended. You might again say I'm splitting hairs, because after all it's just 0.5 of a nanosecond difference between the two, and some of the others which I'll ignore for today. But as I said, this is for a single thread, for a single instruction. So you compound this over millions and millions of calls, and the difference starts to tell. All right. Okay, so that is the benchmark. So that's the code that we ran. This is the cast lock. This is C++ cast lock, compare and exchange. This will compile down to compare and exchange instruction. And using perf, you can always look at the assembly corresponding to this code. This is the unlock, which simply does a store in both the cases. This is the exchange. This will compile down to the exchange instruction. And if you don't get a lock, you spin. Don't get a lock, you spin. Same case here. And for unlocking, you simply store a 0 back. All right. So that's the code that we tested out. And you see, I have a lot more software running today than I would ordinarily when I'm benchmarking. I'll shut everything down. But despite all that, despite all the interference from the recording software and everything that I'm using right now, the difference is still the same. So when I ran this for the slide, the difference was about 0.5 of a nanosecond. And when I ran this today, right now, the difference is not that much. If you play a sport, let's say cricket, then you do a lot of, net practice, wherein all you worry about is eye on the ball and the swing of your bat. If you play tennis, you do a lot of range hitting practice, wherein again, you eye the ball and your swing. That's the only thing that you worry about. But that's different from a math situation. There are no real pressures apart from eyeing the ball and the swing of your bat or racket. When it comes to real matches, you have pressure from the opponent that you're playing, the surface that you're playing on, who's standing on the other side of the net, if it's 10s. Nano bench is a bit like net practice or rallying. So there's no real pressure. So as good as it is for objective benchmarking, the real world is rarely objective. When you have 32 threads vying for the lock, a lot of other pressure comes in, a lot of other dynamics come in that dictate how good or bad you perform. So we're going to take a look at benchmarking under contention when there are, anywhere from 4 to 32 threads on a hardware like this, to check out whether the difference between compare and exchange, does it hold up still? Does the wide gap in, or does it close down? So we'll take a look at that. And for this, we've got many other softwares. One of the foremost of those is Google Bench, very famous, very correctly designed. So let's take a look at the Google benchmark. So the code for lock remains the same. This compiles to compare and exchange. This compiles to a regular store. In case you don't get a lock, you spin. This is the exchange spin lock. Again, this compiles to the exchange instruction. This compiles to a pause. This compiles to a regular store. Here's the actual benchmark. We've got something called a shared state, showing you what a shared state is. It is templating the lock here, and the lock could be one of these. We just test the first two. We leave the other two for the interest of time. And first one is the cast spin lock. The other one is the exchange spin lock that you other saw. Now, this is the actual benchmark code, and you pass this parameter, the state, and the state takes care of various things. So the things that can go wrong while benchmarking, those are the things that not everything, but most of it can be delegated to this Google benchmark and the corresponding state object, right? So, well, from the state, you take the lock out, call the lock function, increment a global counter, which is here, and then you unlock. So this is what we are benchmarking, and those are the two benchmarks we test out. First one is the cast contended, and the second one is the exchange contended. Now the thread is a variable here. The threads are going to vary from 1 to 32 at gaps of, I think, 4 threads. The number of iterations, you take an average of that. Number of repetition, you take an average of that. What you could also do is that you can have some dry runs in the beginning, and which is not configured in this case. And that's about it. Now, when you test this benchmark, well, here are the results. And as expected, exchange performs twice as good when there are 4 threads, about 2.4 times as good when there are 8 threads, about the same 2.47 times as good when there are 16 threads, and about 2.19 times better when there are 32 threads. So roughly the same. So, it kind of pulls ahead a little bit, but doesn't actually run away with it. But because it also has a spin in it. So that's your result for the exchange versus compare and set. So this is the aggregated output. Nothing really that strikes out. We've already discussed how many times better the exchange is, compared to the compare and exchange. And that's exactly what we discussed just now. How many times better? About a little more than two times. So this is your, compare and set, and this is your exchange. Of course, the exchange wins hands down, if you see here. So let's take a look at false sharing. But before we take a look at false sharing, I want you to have a look at the layout of the microprocessor that I'm working on. All right. Now, you can gather this through the ls topology command. ls topo for short. Now, so as you see, this is my RAM, this is my L3, L2, L1 data cache, L1 instruction cache, and the various cores. I've got 8 performance cores. In short, we call them P cores. And I've got 16 E cores or efficiency cores or efficient cores. The P cores can run 2 threads each. Okay, so totaling to about 32 threads is what I can have in flight at the same time on my system. All right. I have another command here, which is watch, and we query this proc CPU info and then grep the megahertz, that means the frequency of the CPU for each of these cores. Now, in the default state, obviously the frequency of the CPU can vary depending on the load that they get, and you cannot tell the difference between the P cores and the E cores. All right, but you have commands with which you can say that, all right, let's not vary the frequency. And when we set that command, approximately the last 16 cores, you will see they don't go beyond 1600 megahertz, and the first 16 they don't go beyond 2002 2.2 gigahertz. All right, but even here, see, there is some variability. The reason for that is the processor P states, and what the processor does, it gets into various states of sleep to save power. Now, as I had mentioned earlier, it's very difficult to do micro benchmarking, and you can see why. So there are subtler and then even more subtler controls of the CPU which vary the frequency of the CPU. So here is what we have then. So this is what we got from the ls topo command. So mine here is a single socket system, and as I mentioned earlier, we've got 8 P cores running 2 threads each and 16 E cores running 1 thread each. This is the memory, the various sizes, everything is mentioned. All right. This is the L3 cache shared among all the cores. This is the L2. The sharing details are different depending on whether it's a P core or an E core. All right. This is the L1D cache. This is the instruction cache, and these are the cores. So your data is here initially, and it's brought up to the registers via L3, L2, L1 data cache, and then the registers. So DRAM, L3, L2, L1 data cache, and while this transfer is happening, the unit of transfer is 64 bytes. So nothing ever gets transferred in terms of bits and bytes. It's multiples of 64 bytes, and this is called a cache line. So when data moves from memory to L3 to L2 to L1D cache, well, the unit of transfer of data is 64 bytes. Now, this is a hardware construct. It's to amortize the cost of transfer, but it's got its own, you can say, behavior, and you got to keep this in your mind. So this is what is known as hardware awareness. So when you're aware of this, you design around it. Now, here's how our current setup is. We have a lock shared by 32 threads, and thread T0 working on core C0, thread T1 working on core C1. So let's assume thread T0 is working here and T1 is working here. All right, this is the same cutout from the same picture here. Your lock is here. All right, and when either of these two threads they fight for the lock, this complete lock structure, the lock is just a part of it, and whatever else is there in the 64 bytes, that complete cache line, 64 bytes, is brought up via L3 to L2 to L1 data cache, before it can be modified. Now, so when a thread attempts to modify, when the two threads attempt to modify this lock, whoever gets to the lock first, so let's say it's thread T1 gets to the lock first, the hardware marks this particular cache line as modified, and consequently it marks this cache, the same cache line loaded in a different cache here, so the same cache line as invalid. So there's a protocol, there's a hardware protocol called messy, single S messy, all right? Right, so modified, exclusive, shared, and invalid. So this one has been marked as modified, this one has been marked as invalid. What that means is this has to be reloaded from the main memory via the same path one more time. Okay, now it's bad enough that because of 32 threads sharing a lock, the moment I get the lock, the rest 31, they have to wait for it. That's bad enough. But what is also happening is that the cache line that was loaded, and maybe this thread and maybe other threads were interested in the structures which are here post that lock. So it doesn't matter. What matters is, and what you have to keep in mind is that once the cache line is marked as invalid, it has to be reloaded. All right, so that complete cache line has to be evicted, and a new version of that cache line has to be loaded from the main memory or from another data cache where the modification had happened. Okay. Now this costs a lot of CPU cycles. So there are two things which are happening here. One is what we call as true sharing, and the second one is what we call as false sharing. Both are bad. It's just that you take different strategies to guard against these. True sharing means the two threads were indeed interested in the same bit or same structure, whatever the case may be, and they are paying a price for it. False sharing is, let's say there's another thread T3 working on core C3, which loads the same cache line but wasn't interested in the lock, was interested in whatever was after the lock. So even this cache, because it's a copy of the same same 64 byte aligned cache line, this also is marked as invalid. So this particular thread T3 had no interest in the lock, at least not at that time, all right? And yet its cache line was marked as invalid, and you had to reload that. So there is true sharing and there's false sharing. Now, to avoid true sharing, we use a technique called striped lock. Instead of having one global lock, you have multiple. In case of HNSW, the structure which is there, which the algorithm which controls the indexing and the search of a vector database. So in case of this, we can have one lock per node. It's not a tree after all, there are no branches. All right, so you can have one lock per node, but we'll get to the HNSW in just a while. Sticking here, right now, what we'll do is that we'll run a benchmark wherein we'll have a single lock and another one wherein we'll have 4 locks. In fact, we don't need this. We just need these 4 locks. Now, if we have a setup wherein we have 4 locks and we have 32 threads, and with some hashing technique, we can have, roughly speaking, about 8 threads going down each stripe. Okay. Now, in this case, we have alleviated a bit of true sharing, but there is still false sharing. Reason for that is, if my lock bit is just 1 bit, this all can be accommodated in, let's say, 8 plus 4. So let's say even if I'm using 1 byte per lock, we'll have 8 4s or 32 bytes, well within the 64 byte cache line. So we have a setup wherein we have 4 locks. We have 4 locks with 8 with 1 byte each, and we have another setup wherein we have 1 byte per cache line. So let's say one lock in one cache line, another lock in another cache line, another lock in another cache line, and final lock in another cache line. So we still have 32 threads in both the cases, but in one case the locks are closely packed together, and in another one they are separated by a cache line size. Now cache line size is 64 bytes, but we separate them with 128 bytes padding. The reason for that is your Intel CPUs, they pull not just that particular cache line that I'm interested in, but even the ones which are close to it. They kind of pull two of them together. All right. So let me summarize what we've just understood. Now, amongst the compare and exchange, obviously we pick exchange. So we pick exchange and we analyze and benchmark false sharing. So what really is happening is we have two separate setups. This is my setup 1. This is 64 bytes and lock 1, lock 2, lock 3, lock 4. And this is my second setup. Lock 1. This is 128 bytes. So lock 1, lock 2, lock 3, lock 4. Now, this might look a bit counterintuitive because this takes more space, but it's supposed to be more efficient. We'll check it out. Now, we use Fibonacci hashing. It's beyond the scope for today. So basically with this hashing function, we have 32 threads, approximately 8 threads going down each stripe. Okay. So there will be some true sharing within these eight threads, and there will be false sharing across these threads because they are all in the same cache line. Now, the way to alleviate true sharing is to go for more stripes. And the way to alleviate false sharing is to ensure that the locks still lie on a different cache line. So this as it is, let's check and let's benchmark these two. So this is the structure. Exchange spin lock with false sharing or with testing false sharing, whatever it is. This is my lock. That's the flag controlled by the lock, and that's the padding. This padding is controlled by this templated parameter. This will be 8 and 128 for two different versions of the benchmark. The rest is all constructor parameters set up. This is the lock and the unlock function. Nothing changes. This is as it is. This is my actual benchmarking function. Take the lock, increment the counter, unlock. So there's a counter, remember. Okay. And these are the two, benchmarking templates. First one, wherein the templating parameter is 128. That's 128. And the second one, wherein it's 8. So here's how things look like. So this is the one wherein we have 8 bytes at these addresses. First lock is at address 0, address 8, address 16, hex 10, and the last one is at 32 or hex 18. All right. The rest of the bytes, there's nothing much in it. And basically we are checking as to how many times in this course of the benchmark do we hit this modified state, and each modified state is going to force cache invalidation. All right. This is the messy protocol I was talking about, messy with a single S. Right. Now, so that's how it looks like. If there are, if there is thread 0 on core 0, if there's thread 1 on core 1, thread 0 core 0 takes lock A, thread 1 core 1 takes lock B. While they are not interested in each other at all, there are two different stripes, two different locks, and yet this cache here will get invalidated. All right. So this is what we call this false sharing. There will be some true sharing between the 8 threads approximately that will go down the same stripe. All right. Now, so can we check this out? Can we benchmark this and can we check this out? Well, of course you can. So this is the command I'm going to be running. And perf gives you a specific command to analyze, to benchmark and analyze and count these modified states. So it's called perf C2C record. We'll ignore these for today. Output goes to that particular file. Well, this is with a padding of 8 and it's supposed to be running slower, all right, than the one which has got padding 128. So again, the same thing here. And I ran these benchmarks just 2 minutes back. So here's the output of that. Now I timed these two, and the first one, of course, you can take a look at the nanosecond that it takes, about 6034 padding of, you can take the mean here, 6042, and the total benchmark took somewhere around 3 minutes to finish. This is with a padding of 8. When I ran this with a padding of 128, all right, well, it is half as slow or twice as fast, and the total benchmark took 128 1 minute 28 seconds. So that's again half. All right. Well, so what about the perf report? Well, perf report is absolute fun to watch. So let's look at the perf report. So here's the perf report. So that C2C report. So when I analyze the report with perf, it tells me that under contention are two cache lines, cache line 0 and cache line 1. The cache line 0's contention is concentrated at addresses 0, 8, 10 and 18. Okay. And the other one is for the counter, so which has got 100% concentration of modified. So there is a lot of true sharing which is happening there. But this is absolutely false sharing, unnecessary. So this is for the case 1. If I had to picturize this, well, that's what it is. So log A, log B, log C, log D, 8 bytes, 8 bytes, 8 bytes, 8 bytes. Addresses 0, 8, 10 and 18 in hex, which is nothing else but 8, 16, 24 and 32. The rest of the bytes are empty here. And the total number of modified lines, the total number of times that a cache line was modified and hence had invalidation to contend with that's a huge number, of course. This is in the total number of modified lines for this particular benchmark, if I had to break it down, 32% for the counter line and 67% for the 4 locks in a single cache line. And that 67% is divided into lock A, B, C, and D. Of course, there's a little difference because of the hashing, you might not have equal number of threads going down each stripe. So that is why these numbers are a little different. And the second line is, of course, the counter line. And the counter line had a lot of true sharing, no false sharing, but a lot of true sharing there. And that's why that stands at 100%. Now, this is case 2, padding of 128. And it tells me that there are total 5 lines in which contention is happening. 5 lines. And lock 1, address 0. Lock 2, address 0 for the second line. Lock 3, address 0 for the third. And lock 4 for the, lock 4 for the fourth cache line, again address 0. So there is no false sharing which is happening. Only true sharing between the threads which are going down the same stripe. Okay, and the last one is for the counter. So there are 5 cache lines, and the proof, as you saw, is in the performance. It's twice as fast. So how do you take this forward? You take this forward by reducing false sharing as much as you can and reducing true sharing as well. Now, in this case, I've got 4 stripes. Now, how many stripes can I afford also depends on my application logic and a lot of other things. So that's probably a topic for another day. And this is what's happening now. So you have to visualize this. Stripe A, stripe B, stripe C, stripe D, 128 bytes each and 1 for the counter. Now, these shared structures. So obviously, the counter is another place where a lot of these hit. So this is half as many hit the modified hits that I'm getting in the previous case. So this is half as many or nearly half as many. So can we reduce them further? Of course. How? Stripe more if possible, if your logic permits. And what about the counter? Can I have a striped counter? Well, we can. Of course we can. So these are the tricks that Usearch and Stillwater use to ensure that your vector databases, they have as less latency as possible and as high throughput as we can get given our hardware. Let's move on. So everything well under control. Of course, you can get better if you increase the number of stripes, but yes, for now, this should do. Right, so side by side, if you compare the two, that's what it is. I think we already discussed this. Nothing much. Again, side by side, that's your case 1, this is your case 2. And this is how the Usearch. So Usearch has got this structure called striped log GT. No prizes for guessing that it uses the exchange and the store for locking and unlocking. And there's a padding of 128 to ensure there's no false sharing. All right. You can get this from the open source link at GitHub for Usearch, but we have added a lot more things to it given the hardware architectures that we support, the specific microarchitectures that we support. All right, now, what about the counter? So can we have a striped counter? Well, of course we can. This code is proprietary, Stillwaters. So I won't show you the code, but the idea is not that difficult to understand. So what we can do is that we can have striped counting. So there's a trade-off here in the design. The trade-off is that you can think of it like a distributed counting. So if I have 32 threads, 8 threads counting one stripe, next 8 threads counting, not exactly 8, but it depends on the hashing, but I hope you get the drift. And each of these stripes being counted parallelly. Trade-off is that while doing a sum, you'll have to sum across these 4 stripes. So that's the trade-off here. Won't show you the code, but that's how it looks like. So the total, so that's the trade-off here. You need to understand the trade-off. So slot 0, slot 1, slot 2, slot 3. And when you bench, so we have done this for every shared data structure which is there in the Usearch. Now we come to the algorithm. All right. So you already have seen the algorithm of HNSW. And this is how the structure is laid out for HNSW. So we'll go through this in a bit more detail. Let's get into a detailed analysis of HNSW logical structure and its in-memory layout. All right, this is the logical layout. Your layer 2, layer 1, layer 0, and as we've discussed already in the past, well, every node is linked in layer 0. Some of them are skipped in layer 1 and so on. Now, you start with a random entry point, find out the neighbor, drill down, and you know where your entry is going to be. So at the time of addition, okay, you firstly drill down the layers and figure out where your entry point is, who your neighbors are, and you fix the pointers up. But before we get there, let's take a look at the in-memory layout. So this logical graph structure, multi-layered graph structure, is actually in memory a flat layout, a flat tape layout. Now this is my node 1042. It's level 2 neighbors, it's level 1 neighbors, it's level 0 neighbors, and so on. So there are a couple of neighbors here. You see there's a node 3. So node 3 would, and its detail would be on the same layout, on the same tape. Node 19, well, this node 12, same thing. Node 19, same thing. So node 12 and its details, node 19 and its details, and so on. So everything is on the same flat layout. There's no fancy structure wherein you allocate. So this tape is pre-allocated, and this shows up in the top level analysis that we've done before. That in terms of memory, the usearch takes marginally more memory right in the beginning. I mean, of course, you get the benefit of it, but in the beginning, it pays the price of allocating this tape well in advance. Okay. Now, there are a couple of pointers here that you have to keep in mind. This is the beginning of the tape. That's the end of the tape. And you have various functions to work out. So for example, you specify the key and it works out the offset of where that key is located. So if I pass the key as 1042, it'll work out the offset of this particular node and so on. Well, the same thing goes for the level as well. So everything. So this is not a traditional, structures of C++. Everything is on this flat layout, and the functions, they work out the offset of where what is, so where level 1 is, where level 2 begins, and so on. And the same thing goes for the nodes as well. Now, so how do we allocate a node here? How do we allocate a node here? So this is how we allocate a node. So once I have figured out that I have to add this node and it has got these, let's say, 2 neighbors, first thing that I do is that we use step 1, use XADD to allocate. Okay. Wait free. Step 2, fix the neighbors. So let's say my neighbor 1 is this element, neighbor 2 is this element, neighbor 3 is this element. No locking so far. So XADD, no one knows about this node yet because it hasn't become visible yet to other threads. Why has it not become visible to other threads? Because it's just been added. Okay, so how do we make it visible? So we make it visible by writing a very special, you can say, a flag here at a particular offset. So if the node starts here, let's say at a particular offset, and this offset is configurable, you add, or so once you fix the outgoing pointers, you now make this particular flag visible with a memory order release. I mean, you just go back to the code that I showed you. The unlock function calls the store instruction with a memory order release. What that means is, once you update this flag doesn't stay in the cache and is immediately pushed to the main memory so that other threads can detect it. So let's recap this. Step 1, XADD allocate. Step 2, you fix the outgoing pointers and you update the flag of outgoing pointers. Now the incoming ones, go to this node and take a lock on this node. This is done using exchange mechanism because it's quite possible that another thread views this particular node as the neighbor. So you take a lock, fix the pointer back, release the lock. That's it. So there are a couple of steps. Let's recap this one more time. XADD, allocate, lay out the structure, mark the outgoing pointers into the same tape wherever they are, wherever the offsets are, write a flag to make this particular node visible. Now take a lock on the nodes which will point back one by one. So let's say if I have got 10 neighbors and those 10 neighbors need to point back to me, we'll go over them one by one, take a lock one by one, and so take a lock, fix the back pointer, release the lock to that node. Again, do the same thing with the next node and so on. Right? So this is what the steps are. So let's recap this step one more time. So the addition has 2 phases. XADD to the end of the tape. All right. We'll show you this code in just a while. And then, so there are 2 phases to this. Phase 1, you simply do an XADD, allocate, layout, write the layout, all right, fix the outgoing pointers, and write a flag. So that flag, and phase 2 has 2 parts to it. So phase 2 has 2 parts to it. Phase A is when you write the outgoing nodes. Once you've written the outgoing nodes, write the flag and write it out to the main memory, which means has a memory order release semantics, just like the unlock function that we spoke about earlier. and this is how it looks like. So new node, pointers pointing to the outgoing neighbors, write the flag so that this particular node becomes visible. Last but not the least, this is where you take a lock on the outgoing nodes one by one so that you can fix the pointers pointing back to this current node which has just gotten added. So that's about it. Let's profile and see if that's true. So if you recall, we had looked at this, we had gathered this data, but we hadn't looked at the stack. So this is the one that we had ran a while back. So it's time to take a look at the stack that is in flight while the utilization is not that good. So that's the stack, and what we can do is we can look at perf once again, and we can help perf look at the assembly for this function. So basically there are two functions, index and add, and I've already kept it ready. So these function names are pretty long if you look at the name because of the templated parameters. So there are two functions here. This is the one where the allocation happens from the tape, as I was talking about. So this function is called index dense GT, and while it would be worthwhile looking at all these hotspots that are marked in red, well, I guess not for today. So that's your lock XADD for memory allocation, not memory allocation really, allocation from the pre-allocated tape as we spoke about. So this is the phase 1 as we had discussed earlier, and phase 2 is in case there is interference, you lock the incoming, so you lock the nodes for which the incoming pointers have to be fixed. So this is the other function. So, all right, so that about 26.80% of the time exchange. There's no lock here if you see. There's a lock prefix is not used. That's because exchange has got an implicit lock built into it. All right, so on that note, we'll wind up the discussion on Stillwaters Usearch as far as the algorithm and the benchmarking is concerned. So I hope we'll take a look at the comparison between FAISS and Usearch. You have looked at it, but here are some numbers from the open source. Now, this is the construction speed. So when you do index, well, as you can see, the bold lines are for Usearch and the dotted line is for FAISS. We have done a lot of work on it. So the difference between FAISS and Usearch, Stillwater Usearch, is a lot bit more than what you see here. So that's your construction speed, and it's about 19x speed advantage, unheard of. Okay, this is the search speed. So post that 4 to 5 million mark, well, again Usearch surges ahead and FAISS falls behind. About about 32 million mark is when FAISS's application performance goes down the hill completely. All right, so there's a 189x speed advantage. This is on the open source. We have done a bit of work on this, quite a bit of work on this, and this goes beyond 220 on the architectures we support. Again, this is your construction speed for for a 1500 strength vector. So that's a dimension vector. So 1500 dimension vector. Well, you see the difference again is huge. Okay, so search speed, again, this is a comparison of the search speed, bold line Usearch and the dotted line FAISS. So that's the speed that you get, 233x, around 400x and 500x, depending on the type of data that you're looking at. All right. So this is the Stillwaters based on Usearch. We've done, like I said, we've done a lot of work on this, and that's the kind of speed advantage that you're looking at. Now think about it this way. If this is the benefit that you get with your hardware awareness for a vector database, imagine what can you gain if similar tactics can be applied for LLM training and inferencing. So let's take a look at that. So finally we come to the end of it. Remember, sometime in the beginning we had made that Venn diagramish illustration where we said algorithms, hardware awareness, software, and observability tools. We'll make that drawing one more time, but with those fields filled in. So, on the hardware side, some of the instructions we saw today were compare and exchange, XADD, exchange, and a couple of them that we missed, but that's the whole idea. Lock OR and lock add are very similar to XADD and exchange. So if you've gotten those two, a little read up on lock OR and lock add would set the matter straight. We didn't look at the PTX today and the tensor core today, but in a session very similar to the one that we've had today, we'll extend the learning on the GPU side with similar tools and analyzing, let's say, an LLM kernel, and therein, the PTX information, the PTX knowledge, and tensor core is going to come in very handy. On the algorithm side, today we looked at skip list, HNSW, wait free logs, and skip lists. Okay, and hope it all made sense to you. If you have any questions, you can mail us or you can also comment. My team will respond to it. On the software side, we looked at VectorDB today, but as I said, sometime in the future, we'll look at LLMs inferencing and training in great detail. Last but not the least, those are tools that we spoke about today: Perf, TopLev, FlameScope, FlameGraph. We didn't look at Stillwater Tracer today. Hopefully, it's going to make its entry in the next session or the one after that. Now, sample this. In a vector database, we're talking about speedups of up to 250x, 400x, 560x. Now, if we talk about these kind of speedups with the tricks that you've seen, if we can extend them to the GPU side, so imagine the kind of speedups that you're going to have if similar tactics can be applied to LLM inferencing and LLM training, because there the scale is absolutely massive. So even a few times speed up can save me millions of dollars. Okay, we would hope to see you soon in a session like that. So I hope you enjoyed the session as much as I did bringing it to you. I'll first, I would like to extend my thanks to my team, which helped me prepare for a session like this. And I'll say this, that in not so far ahead in the future, we'll bring a very similar session for LLM inferencing and LLM training, which is also a part of the course that is being created and curated by Stillwaters and IITs. So thank you very much and see you next time.